Welcome back. Today we're going to be talking about proportions from tables and graphs, day number 1. Our content objective is students will be able to determine proportionality from tables and graphs. Language objective is students will be able to explain in words the reason for proportionality from tables and graphs. And why am I learning this? Well, it's important for many real-life problems like finding the total cost given a unit rate and initial value. First, we're going to go over some background knowledge. If you recall from 5th and 6th grade, you did practice graphing order pairs on a coordinate plane. So first number is going to tell you to go right, and the second number is going to tell you to go up. So in other words, you can also refer to them as input and output. So x comma y. So here, if I wanted to graph 0 comma 0, it doesn't go anywhere, so it will just be right here. It's not going to go right, it's not going to go up, so it starts at the origin. Second number is 5 comma 3, so I'm going to go to the right 5, 1, 2, 3, 4, 5, and then up 3, 1, 2, 3. Next number is 10 comma 6, so we're going to go over 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then up 6, 1, 2, 3, 4, 5, 6. 15 comma 9, so at one point you're going to start realizing, okay, I can count all the way to 15, or I can just see that here is a marker for 15. And then if I want to go up to 9, here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So here, I can graph them, and I can just go ahead and connect the points, and that would be my line. So let's go ahead and look at number 1. It says the following table shows a relationship between the amount of cherries in pounds and costs. Is this a proportional relationship? How do you know? The answer is yes. Why? Because there is a constant of proportionality, aka the multiplier, which just so happens to be 1.5. Let me prove it to you. If I do 1 times 1.5, that'd be the $1.50. 2 times 1.5 would give you the $3. 3 times 1.5 would give you $4.50. And 4 times 1.5 would give us $6, and so on. So the number of pounds determines the cost. So why is this important? Because we need to know what is considered the input and what is considered the output. The input is the independent information, and then the output is the dependent information. So since cost depends on the number of pounds, cost is the output. It is dependent, and the amount is the input because it's independent. So here, in order to figure out the constant of proportionality, aka the multiplier, what we want to do is set it up as output over input. So here, we could set it up as $1.50 over 1, $3 over 2, like we did here, $4.50 over 3, like we did here, $6 over 4, which is right here, and $7.50 over 5, which is here. You're going to find that all of these will reduce to $1.50. So that represents the unit rate. It means that it costs $1.50 per pound. If you're not sure how we got the units in the order that we did, if you left the units here, for example, for 150, it was the cost, so you would put dollars, and then here the 1 referred to the pounds. So here you can see it's $1.50 per 1 pound. Actually, there's no S there. There you go. So part B, it says, put the information from the table on the graph below with the amount of cherries on the x-axis and the costs on the y-axis. Put these labels on the graph. So they said the x-axis is going to be the amount of cherries, and the cost is going to be the y-axis. Okay, so let's do that. So the input, aka the x values, are going to be the amount of pounds. Input, once again, tend to be the independent information. So here, we're going to go ahead and put the output, and these are the dependent cases. So again, cost depends on how much you buy. So here, now that I've labeled my graph, I can go ahead and record my information. But actually, before I do that, it might be a good idea to actually label to see what each tick mark is going to represent. Here, I'm going to go ahead and mark it like this, and for the output, since it goes up to 750, I'm going to go ahead and mark every 2 by a 1. So now that I have this, I can go ahead and graph. So for 1 pound, which is right here, it's going to cost $1.50, so that's going to be right there. For 2 pounds, that's going to be 2 pounds on the x-axis. It's going to cost $3. So I'm going to go all the way up to $3 for the cost. For the third one, it's going to be 3 pounds for $4.50. So for 3 pounds, it's going to cost $1, $2, $3, $4.50. For the 4 pounds, it's going to cost $6. So we're going to go over to 4 pounds, and it's going to go up to $6, which is right here. And last but not least, for 5 pounds, it's $7.50. So for 5 pounds, we're going to go up all the way to 7 and then 50 cents, and that would be our graph. So here's what we know so far. Proportional relationships have a constant multiplier, which we refer to as the constant of proportionality. If ratios of the output over the input are equivalent, then the simplified ratios represent that constant of proportionality. So let me go back real quick. So if you recall from earlier, you'll notice as we set up the output over input, all of these would equal 1.50. So that ends up being the constant of proportionality, which just so happens to be the unit rate. Now, with the exception unit rate has units, the constant of proportionality does not. All proportional relationships are linear and go through the origin. What does that mean? Well, if it's linear, it basically is a graph that is a line. In fact, if you look at the word linear, you'll even see the word line. Next, what is the origin? The origin is the ordered pair 0, 0. So what does that look like? Well, let's quickly go back into the previous graph that we had to see what that looks like. So here, I would call this linear. Why? Because this graph is a straight line. Now, does it go through the origin? The answer is yes. The origin is right here, which is 0, 0. So because it's both, this is definitely a proportional relationship. Let's take a look at number 2. It says the following table shows a relationship between the number of ounces in soup cans and cost. Is this a proportional relationship? How do you know? So here the answer is no, because the multiplier is not constant. Okay? Here, first of all, you need to understand that the amount is what determines the cost. Okay? So we actually are trying to figure out how does 8 become $1? Well, 8 would have to be multiplied by 1/8 to get that. And 16 would be multiplied by 3 over 32. So already these multipliers are not the same. Okay, if you wanted to check for just to be 100% sure, you would see all of these actually have different multipliers. So here, let's remind ourselves. The number of ounces is what determines the cost. So the number of ounces is your input. It's independent. And the cost is your output. It's the one that is dependent on the amount. So here, if we set up the ratios as output over input, we would have 8 over 1, which doesn't happen to equal 150 over 16, because that reduces to 3 over 32. This reduces to 1/12. And again, you'll see that all of these do not equal each other. So therefore, it is not a proportional relationship. So real quick, let's graph the information on the table using the labels for the x-axis as the amount of ounces and the y-axis for the cost. So x-axis is the amount and y-axis is the cost. So here I'm going to go ahead and label the amount of ounces by 2, so 2, 4, 6, 8, etc. You'll notice I marked every 2 lines, but this is technically going by 2s. Please don't think that because the first number was a 4 that all of these are going by 4s. They're actually going by 2s. And for the cost, since it ranges all the way to $3, I'm going to go ahead and mark every other with a whole number. So now that I have that, I can go ahead and graph. So here, for 8 ounces, it's going to be $1. So notice this is the ounces, so I'm going to go up to 8 ounces. It's going to cost $1. Here, for 16 ounces, it's going to cost $1.50. So 16 ounces is going to be $1.50. 2 ounces is going to be 24. So we're going to go to 24 ounces is $2. So we're going to go for 24 ounces. That's going to cost $2. Next is 30 ounces, which is $2.50. So we're going to go to 30 ounces, which is $2.50. And then 36 ounces, all the way over here, which is $3, which would be right there. So if you draw a line, you're going to find that it's not linear, which is part of being a proportional relationship, and not going through the origin. Quick reminder, here is your origin. The line is definitely not going through this point, so therefore it's not a proportional relationship, even though it was linear. It also has to be going through the origin, which it is not. Number 3, why don't you go ahead and pause the video and try this one by yourself. So for number 3, it says the following table shows the pounds of meat on a sandwich and the calories in the sandwich. Is this a proportional relationship? How do you know? The answer is no, because the multiplier is not constant. Here, for the first part, the multiplier is 1,120. The second multiplier is 650. Already, they're not the same. I don't have to go any further. Real quick, the number of pounds is what determines the calories. So I'm going to go ahead and say the meat in pounds is the input because it's independent. The calories would be the output because it's dependent on the number of pounds, because depending on the number of pounds will determine the number of calories. So now that we figured out output and input, I'm going to go ahead and write all of these fractions. We're going to have the 560 over 0.5, 650 over 1, etc. You're going to find that these do not equal each other. So for that reason, it's not a proportional relationship, but let me show you graphically as well. So we're going to go ahead and label the axes. The x-axis should be the input, which is going to be the meat in pounds. The y-axis should be the output, which should be the calories. So depending on the numbers here, I'm going to go ahead and go by 0.5 on the x-axis, and for the y-axis, we're going to go ahead and go by 50s. So again, even though every 100 is marked, you'll notice it's marked with every 2 lines. So therefore, it's 50. For example, it's 50, 100, 150, 200, 250, etc. So now that I have that, I can go ahead and graph. So for half a pound of meat, it's 580 calories, which is around maybe right here. For 1 pound of meat, it's going to be 650, so that's going to be exactly right there. For 1.5 pounds, it's going to be 740, so that's going to be 750, so it's just going to be slightly below, and so on. So here, graphically, what you're going to notice is it's not linear. Some of you may look at this and say, oh yeah, it is linear, but you'll notice here it's slightly off. And the reason why we can't clearly see it is you'll notice we're going by 50, so it's not as precise. Now, if you were to zoom in, you would be able to see a little more clearly that this is slightly not that straight. So here, since the graph is not linear and it doesn't go through the origin, just a reminder, the origin is right here. The graph is definitely not going through that point. We're going to say that there is not a proportional relationship. The following table shows a relationship between the amount of grapes in pounds and costs. Is this a proportional relationship? How do you know? The answer is yes. Why? Because the constant of proportionality, aka the multiplier, is 0.75. For example, for 1 pound, it costs 75 cents. For 2 pounds, it costs $1.50, and that's being multiplied by 0.75. 3 times 0.75 is $2.50. 4 times 0.75 is $3, and 5 times 0.75 is $3.75. Since all of these have a constant multiplier, it is a proportional relationship. So here, since the number of pounds determines the cost, we're going to go ahead and call the amount of pounds the input because it's independent, and the cost is the output because it depends on how many pounds it is. So once again, if you set up your ratios of output over input, you're going to find that all of them equal the same value, which just so happens to be 0.75. So here I would say the unit rate is 75 cents per pound. If you're wondering how we got that value, simply include the units back into your number. So here, this was referring to the cost in dollars, and this one was referring to the pound. So here you can clearly see it's 75 cents per 1 pound. Now we're going to go ahead and graph the information. It does specify that they want the amount of grapes on the x-axis and the cost on the y-axis. Now you're typically going to see this with all graphs where the input is the x-axis and the output is the y-axis. So on this graph, the input is the amount of pounds and the output is the cost. So I'm going to go ahead and put the x-axis by the following. So it's technically going by 0.5. And the y-axis is also going to go by 0.5. So we're going to fill in our graph by 1.75 cents. So it's slightly here. For 2 pounds, it's going to cost $1.50, which is going to be right here. For $3, for 3 pounds, it's going to cost $2.25, which is approximately here. For 4 pounds, it's going to cost $3. And then for 5 pounds, it's going to cost $3.75, which is approximately here. So if you draw that line, what you're going to notice is it is linear, which is perfect. It's a straight line, but it also goes through the origin. So because it met both requirements, this is a proportional relationship. So guess what? That concludes our lesson for today. Thank you so much for tuning in. And as always, until next time, bye.